Saxon's Trig, lesson 119, is about Descartes' rule of signs, upper and lower bound theorem, and then irrational roots. So Descartes was, of course, a mathematician of the past, and he discovered a correlation between when the signs between terms change from positive to negative or negative to positive, that had a relationship to how many answers or roots the problem had. So this first part is Descartes' rule of signs. So let's jump to example 1, where it says discuss the number of possible positive, oh goodness, let's try that again. Discuss the number of possible positive real roots. So his formula idea works for positive answers, not for negative answers. So that's why they're clarifying possible and positive real roots. So what they're giving us is x to the 5th minus 2x to the 4th plus 3x cubed minus 5x squared plus x minus 2 equals 0. All right, so here we went from a positive to a negative term. That's a change. Here we went from a negative to a positive term. That's a change. From positive to negative, that's a change. From negative to positive, that's a change. From positive to negative, that's another change. And then, of course, there's no other numbers to test. So how many changes do I have here? 5 changes. So this tells me, according to Descartes' formula here, that I can have possibly 5 positive roots. But it goes a little further than that. It can also have, and it goes down by odds. So 5 3 roots or 1 root answer. So this formula will either spit out 5 answers, 3 answers, or 1 answer, just depending. And we're not asked to find them. We're just using his lovely changes in signs to help us figure out how many answers we can possibly have. So in example 2, it gives us 2x to the 5th plus 3x to the 4th plus 4x cubed plus 5x squared plus x plus 2 equals 0. So I have positive to positive to positive to positive to positive to positive. Oh, I have no changes. So since I have no, just a second. Oh, I need to read the problem more carefully. Discuss the number of negative real roots. So his theorem works exactly from the equation here, but if I'm testing negative roots, everywhere I have an odd exponent, I'm changing the sign. Because if I throw in negative x here, that changes that to negative 2. But if I throw in a negative here and I take it to 4, an even number, it still comes out positive. So this one is still positive 3. When I plug in, that's odd, so that's going to go to negative 4. When I plug in here, that's even, that's going to be positive. When I plug in negative, that's going to be an implied negative 1, and then that one is still a positive. Now I can do the same thing. How many changes? Negative to positive is a change. Positive to negative is a change. Negative to positive is a change. Positive to negative is a change. And negative to positive is a change. I've got 5 changes again because it was negative. So I can have 5 negative roots, and then the same thing applies going down by odd numbers. I can have 3 negative roots, or I can have 1 negative root. And those describe the kind of answers, oh, I guess I didn't box that one, that I can have for that. Now, part B, upper and lower bound theorem. To start this discussion, I'm going to start with an equation that they use here. Y equals x to the 4th minus 13x squared plus 35. Now, if we were using our what is the highest number, 35, and adding 1 to find our circular region of interest, that would be 36. Well, that's huge and probably not very helpful. So then, to kickstart the discussion, they say, all right, let's look at the actual graph and see what happened when it was graphed. Well, this number's really super high up here, so we're just going to say that it's like 32. You can see on their graph, oh, yeah, that it's just, I think they're doing it by tens. Yeah, by tens. And so it's 32, 33, something like that. Doesn't really matter. And then they have discovered that everything is falling by doing synthetic division, plugging in all the numbers, etc. They end up determining that they have a number that's falling before the 5, that this was their high point up here, and that in between the 1 and the 2, I believe, they've got a dot down here in the negative. Same thing is happening here. And so they're getting a shape that is basically, I don't know what that dot was. Randomness. Okay, they're getting a shape that is basically doing this. All right, so now that they've actually graphed it, they're saying that they know that their window is closer to the 5 and the negative 5 as their region of interest. So basically, they're almost working it backwards. They're using the graph to get you back to what they're talking about. So they're saying that they decided to use synthetic division to test all of the numbers in between the 0 and the 5. So if you do that on the top of page 653, you're testing the positive numbers, and they tested 1, 3, and 4. 1 gave them an answer of 23, and 3 gave them an answer of -1. Oh, my graph is off. So it should have been more over here. And then 4 gave them an 83, so it was way up there. And then they tested the same thing with the negatives. When they plugged in -1, they got positive 23. When they plugged in -3, they got -1. That would have been a little, should have been wider basically then. And then when they did -4, they got a huge 83, so they knew it was way up there. And so that's how they were plugging the numbers in to get more of their actual graph. So to be more precise, rather than going up to the 5, they were saying that when they used the 4 and got a very large number, it was no longer a good region of interest, so go a little tighter. When they did 3, they got the -1. That's closer into the ballpark. So the 3 and the negative, well, hang on, 3 was definitely for the upper, the tighter one. Now let me look at their negative numbers. -1 gave 23. Again, that's pretty far off. -3 gave -1. That's what I thought. So between 3 and -3 was a much better, using an upper and lower bound for their answers to say what their region of interest was. Okay, so in example 3, use upper and lower bound theorem to find an upper and a lower bound for real roots of the equation x squared minus x minus 21 equals 0. So we're going to just start with positive numbers 1 and 2 and 3 and 4 and test with synthetic division, and then do the same with the negatives. So I'm going to kind of use theirs. All right, let me just test the 1. So that would be coefficients of 1, -1, -21. Dropping the 1, 1 times 1 is 1, adds to 0, 0 times anything is 0, so -21. That's kind of far out there, so not a good upper bound. Let's test 3. So 1, -1, -21, dropping 1, 3, 2, 6. It's still negative, 15. And so that's still kind of far out. All right, so let's try another one. Let's do, let's see, we just did 3, 5. So 1, -1, -21, drop the 1. 1 times 5 is 5. That adds to 4. 4 times 5 is 20. Okay, so that gives me -1. That's pretty tight. But the other part I have not said is that even though this is tight and much smaller, I'm feeling happier with my choice of 5. I'm not sure that it's actually my bound because I still have a change in the signs. I want to find, so that's the other part that the theorem says, is that you're looking for the solution that stops giving you negatives. So since I still have, not negatives, but a change in the sign. So since I still, when I tested 5, if I had gone back and only done 4, I probably still would have had this. So let's go up one more. Let's test 6. 1, -1, -21. Dropping the 1. 6, 5, 30. Now they're all positive. I've had no change in sign. So 6 is a good upper bound because there's no change in the sign. Now we want to do the same thing in the lowers and test those. Since 6 kind of worked, I don't want to jump to -6, but I might want to try -5. Just trying to lessen my, now according to what they're going to say, you need to start at -1, do -2, -3, -4, -5, because you're looking for this one, an alternating sign pattern. You want a positive, negative, positive, or negative, positive, negative. And once you find that, you have your lower bound. But I'm kind of using what I found for the upper to help me try to find the lower. If -5 works, you would have to test -4 to see if it worked, and then you would have to backtrack to -3 to see if it worked, until because you've got to find the first one where the pattern isn't. So whether it's good to do my way or always start with -1, -2, -3, your call. All right, so we've got still 1, -1, -21, drop our 1, -5, -6, +30, and that's going to be a +9. So I am alternating here, so -5 does work. And like I said, I should check to see if -4 works. Now using theirs, -4 spit out 1, -4, -5. So it's not alternating, so no, it doesn't work. So then yes, I know I can keep the -5. So for the upper bound, you're looking for signs that are all positive, and for the lower bound, you're looking for alternating positive and negatives. So let me see here. Yes, so I was looking to see exactly what the question asked for to find the upper and lower bound. So basically your answer here that you would say is you're going from -5 to 6 as your region of interest, your upper and lower bound. All right, they don't stop there. They do another example. Example 4, use the upper and lower bound theorem to find the roots of the equation of x cubed minus 21x plus 20 equals 0. Okay, so technically I should test the coefficients. 1, I don't have an x squared. Single x is -21. No x is 20. All right, 1, 1, 1. Oh, hallelujah. My first test gave me a 0. Use the upper and lower bound theorem to find an upper and lower bound for the real roots of that equation. So since 1 gave us a 0, we know it's not the upper bound because I have to have an answer in that part to know whether I have all positives, but I also know that it got thrown out as soon as I had the negative here. So then, although they're supposed to test 2, 3, 4, and 5. They chose to skip the 2 and the 3 for whatever reason, and they're jumping to testing 4. So 1, 0, negative 21, and 20. Drop 4, 4, 16, 5, 20, and they got a 40. So now they have all the signs. Oh, wait a second. That was negative. That was 0. Help us all. So again, 4 is an actual root answer here, and it also got thrown out because of that. So then they test the 5. 1, 0, negative 21, 20. Drop the 1. 5 times 1, 5. 25, 4, 20. There we go. Now I have all positives, and so I know that 5 will be the upper bound. And then I should test the negatives starting at negative 1 and negative 2, negative 3, negative 4. Okay, but because they're kind of now doing what I did, which is if 5 was the upper, let's try negative 5. And when they tested negative 5, 1, 0, negative 21, 20, drop the 1, negative 5, positive 25, 4, negative 20. Oh, they got a 0, so they couldn't use that one. So I would go backwards and then test the negative 4. When they did, they got... Oh, well, their answers were 1, negative 4, and negative 5, so it wasn't an alternating pattern, so they couldn't use the negative 4. And then when they tested, so they were like, okay, we have a problem going down with the negative 4. When we test the negative 6, they got positive, negative, so they found their alternating pattern at negative 6, so they were saying they can go from negative 6 to 5. Is that what the division of 5 yields all positives less than 5? Yeah, we already found that. Negative 5 is a root, right? So there are no real roots less than 5. Okay, so yes, I could say that the lower boundary goes from negative 6 to 5, but they were clarifying that because we ended up with a root, in other words, at negative 5, they had a 0, so they felt like whatever else was happening, it was either falling to this or climbing to this because it was a 0 root. And therefore, there's not going to be something else happening. It's going to be big or small, depending, even though negative 6 did give them the correct alternating pattern. So I hope that that's being clear why they changed their wording there. Now, let's move on to their short little section C, irrational roots. So they're saying that they have, in all of their other stuff from before, they have been giving real root answers and not crazy complex. Now, we had the one where we had a decimal, but we've not been using imaginary numbers anywhere in any of this. So the list of possible rational roots is determined by the rational roots theorem. There is no similar theorem for finding the list of irrational roots because they're so weird, they're kind of stuck out there without their own little formulas. Those roots can only be estimated by using other methods. And if the value of a polynomial is positive for some real value of x and negative for another value of x, we know that the polynomial will have a value of 0 for some x between those two values. Ugh, wordiness. Basically, here's all they're saying. If you have a dot that's in the positives and a dot that's in the negatives, somewhere you're going to have a place where it crosses the x-axis. You're going to have a 0 somewhere in there. And maybe it's irrational or maybe it's rational, but they're talking about it in the irrational section. Okay. Coordinates, all right, yep. The procedure used in the past for finding irrational roots required paper and pencil calculations, and it was long and involved. Now, computers or graphing calculators can do this quickly for us. So basically all they're saying is if you have one dot in positive, one in the negative, you're definitely going to have a root somewhere in between them, and there is no nice way to find irrational answers.